Alright, so hello and welcome everyone. This is the fourth week of interactive live sessions for the course on Computational Fluid Dynamics for Incompressible Flows. So as you already know, this course is being offered by NPTEL. It's being instructed by Professor Amaresh Dalal from the Department of Mechanical Engineering at IIT Guwahati. My name is Debjit. I am a PhD scholar at IIT Madras and the TA for this course. And like every other week, we shall be solving some sample problems together. So without any further ado, let's get started. Okay, so someone is asking to record the session. It is being recorded right now and it will be uploaded in YouTube. You can get the link from the course page, or I can point you to the YouTube video link as well. So anyway, so coming back to the questions, we have question number one, which is asking us which of the following types of equations are typically solved using the point Gauss-Seidel method. So this is one of the methods which we learned in the lectures of week 4, which is primarily so this question is asking us what type of equations are primarily solved using this method known as the point Gauss-Seidel method. Is it option A, elliptic equations? Is it option B, parabolic equations? Is it option C, hyperbolic equations? Or is it option D, none of the above? So read the question carefully and try to figure out the correct solution. And once you have done so, please type it in the chat box, or you can unmute and answer as well if you feel comfortable. And if you have any doubts regarding the question or anything else, please don't hold yourself back. These sessions are meant to be as interactive as possible. So just go ahead and shoot your questions. Not only questions, any remarks, comments, anything. Okay, so coming back, we have 4 quick responses, all in favor of option A. Let's see what others have to say. So the crowd as of now is in favor of elliptic equations. Let's see what others have to say. I would strongly urge everyone to send in their responses. Okay, so let's have a look at the solution. The answer is indeed elliptic equation. So all of you who chose option A, well done, you did it correctly. So just to revise a little bit, what is point Gauss-Seidel method? So let's say if we have a square domain like this, we divide it into grids, of course, and let's say we want to solve for some physical quantity at this point, which is I comma j. We take 4 other uh, points surrounding it, which are of course I plus 1 comma j, I minus 1 comma j, I comma j plus 1, and I comma j minus 1. Then we, so elliptic equations are usually of the form like this. So dou 2 phi dou x square plus dou 2 phi dou y square equal to either 0 for, so this is, if this is 0, so this is known as a Laplace equation, or if this is some value, then this is known as a Poisson equation, right? So let's say for the case of Laplace equation, we discretize it and convert this PDE, a partial differential equation, into a finite difference equation, which looks something like this. So this would look something like, let's say, so if we do this, then this becomes phi I plus 1 comma j plus phi I minus 1 comma j minus 2 into 1 plus beta squared phi I comma j plus beta squared into pi j minus 1 plus pi j plus 1 equal to 0, or some constant in case of a causal equation. So this is the equation which we then solve, and so this is the equation which we have to solve, and one of the processes of solving that is this point Gauss-Seidel method, in which, let's say, the phi ij is something we are trying to solve. In that case, so we will solve phi I comma j at the k plus 1th level using these other four quantities. So this will now become, uh, so it will have this 1 by 2 1 plus beta squared, then all these other terms over there. So I plus 1 comma j plus I minus 1 comma j plus beta squared I j minus 1, and again beta squared I j plus 1. And while we are doing this, so at the k plus 1th level, that is the unknown, we already have known values which are already calculated. So I minus 1 and let's say this I j minus 1, they have been previously calculated. So we will use the previously calculated values, the updated values at the k plus 1th level, 1th iteration, and the for the I plus 1 comma j and I comma j plus 1, we still have the known quantities from the previous iteration, so we will use them. The previous iteration is the kth iteration, so we will use that, and this is the point Gauss-Seidel method, if you will. So this is how we solve elliptic equations using the point Gauss-Seidel method. Any doubts on this? Any questions on this? Everything is clear, right? Okay, so simple stuff. We will keep moving along. We'll move on to question number 2 now, which is asking us which of the following iterative methods is known for its simplicity but slow convergence. So there are pros and cons to it. So this is the pro and this is the con over here. So the pro is it's a simple method, but the con is its convergence rate is slower than other known methods. So is it option A, point Gauss-Seidel method? Is it option B, line Gauss-Seidel method? Is it option C, SOR method, which is also known as, so the full form is successive over relaxation method? Or is it option D, Jacobi method? So which one is it, A, B, C or D? Point Gauss-Seidel, line Gauss-Seidel, successive over relaxation, or Jacobi? Okay, we have a few quick responses, all in favor of option D, the Jacobi method. Let's see if anyone else has anything to say. We have 1, 2, 3, 4, 5 responses. Good. I would urge everyone else to send in their responses as well. So question 2 of today's session is asking us which of the following iterative methods is known for its simplicity but slow rate of convergence. Is it option A, point Gauss-Seidel? Is it option B, line Gauss-Seidel method? Is it option C, successive over relaxation method? Or is it option D, Jacobi method? Okay, so we have a few more responses now, all in favor of option D. So let's have a look at the solution, and it is indeed option D. Well done. So Jacobi method is a simple method in which, uh, let's say, so we wrote down the discretized equation in the last slide as well. I'm not repeating that. So that equation is true for all the points within the computational domain. And if we arrange them into a matrix form, all the multiple equations, if we cast them into a matrix form, so then it becomes one coefficient matrix A into a vector phi, which is at k plus 1. So this is the unknown vector field which we are trying to solve, and this should be equal to another uh, you know uh, vector which is of the form, let's say, b, which b again is a function of some these phi quantities at the previous iteration at the kth level, right? So if we now simply, so this becomes basically a phi k plus 1 equal to b, or I won't write this k plus 1 now, it's a phi into b, and phi we can then write as a inverse into b. So simply doing this would give us the next iteration value of p, and we will keep on continuing this until the error becomes small enough, which is a telltale sign of an iterative method in which we don't directly do things, we iterate again and again. So here the problem is this Jacobi method, although it's simple, but its rate of convergence is slow, because in the known quantities we only use the quantities whose values we already know. Now, as we saw in the point Gauss Seidel case in the earlier slide, so if I go back, so here you can see that for, okay, let me use a different color of ink here. So this quantity and this quantity we use at the k plus 1th level. So we are already updating those numbers as we are going. Now in Jacobi method, instead of using k plus 1, we simply use those values at the kth level every time. So that's why since we have updated values but we are not using them, that's why the rate of convergence is slower, because we are losing out on important information. But then again, coding this is simpler because of the methods are very easy to carry out. So that's why the Jacobi method is simple, but the rate of convergence is slow. So that is again the reason why Jacobi method isn't used much popularly anymore. The other methods have replaced it. Okay. Any questions on this? Okay, so if there are no questions, we will move along. We'll move on to question number 3 now, which is asking us what is the primary advantage of using over relaxation in iterative methods. We saw the example of successive over relaxation method in the previous question. Now, the question is, why use over relaxation at all? What is the main advantage that it gives us? Is it option A, more accurate solutions? Is it option B, faster convergence? Is it option C, greater stability? Or is it option D, none of the above? Okay, we have one quick response in favor of option B. Let's see what others have to say. So does over relaxation give us more accurate solutions? Does it, uh, you know, accelerate our convergence? Does it stabilize the solutions, or is it none of the above? Okay, we got a couple more responses, all in favor of option B. Let's see what others have to say. So all of you should send in your responses in the chat box. That's what I'll keep on urging again and again. So it's very important to really engage in these questions and participate in it. I know the questions are simple, but sometimes we need this simple practice as well, just to, you know, uh, uh, so this will help you in solving the assignment questions as well as the final exam as well. Okay, one more thing. If you have any doubts with previous assignments, you can ask them here as well. So this is a good forum to discuss those problems. Okay. Anyway, coming back to question 3, we have a few responses, all in favor of option B, which is telling that it should converge faster if I'm using an over relaxation method. So if we look at the solution, it is indeed true. So over relaxation does give us faster convergence. So what's the idea here? The idea is that we are going from the kth kth solution to the k plus 1th solution at each iteration, and every time when we there is a method of calculating this k plus 1 from k, so there is this difference, right? So there is this difference which we are sort of adding to the previous value every time, right? So this difference is being added every time, and we are progressively reaching towards the converged solution. So the idea behind over relaxation is that why not increase this difference by a little bit, even by a little bit. If we increase it, so let's say this is our starting point at phi 0, and let's say this is our end point phi c, which is like phi converged, and we're going from step by step. So let's say this is phi k, this is phi k plus 1, this is phi k plus 2, and we keep going towards the converged solution. So the idea behind over relaxation is that we are covering this much distance, right, in one iteration. So why not increase this distance by a little bit? And that is the over relaxation factor which we include here. So this omega in over relaxation is usually greater than 1, but not greater than 2. So we can't get greedy. If we over relax it way more, then it may so happen that we can overshoot the converged solution, and then we'll have to come back again. So that's not preferred. So it's important to keep the over relaxation above 1, but not too much greater than 1. So this is the core idea behind over relaxation, and as a result it improves the speed at which we converge. The number of iterations taken is reduced. Okay, but this is a primary advantage, but there are some disadvantages as well, which we will see later. Okay, any questions on this?
Okay. Okay, sir. Understand.
Okay. Anyone else? Anything? All right. So if there are no questions, we'll move along. Now, this is so here three statements are given in options A, B, and C. You will have to pick out which of these following statements is true regarding. So this is all these have a common theme. This is regarding under relaxation in iterative method. So we saw over relaxation, in which this over relaxation factor is greater than 1, and under relaxation is it's less than 1. This is also used in some cases. So what are the statements given here? So statement A says that it can lead to faster convergence than over relaxation. Option B is it can reduce the magnitude of oscillations in the solution. Option C is it is only applicable to nonlinear equations. And option D is both A and B. So I should add sometimes over here. So which of these statements are true? We have a few responses, couple of them in favor of option B and one in favor of option D, that is both A and B. Let's see what others have to say. Another in favor of option B. Okay. Another in favor of option B. More responses are in favor of option B. Now, a response in favor of option D, which is saying that both A and B are true. Alright, so let's have a look at the solution. And it's actually option B, that is both A and B. So both A and B are true over here. So let's. So the main reason why under relaxation is used is that. So this is something which I briefly introduced in the over relaxation question. So let's say if I over relax. So if this is my solution. So okay, I'll draw a graph maybe. So let's say this x-axis is the error. Sorry, the y-axis is the error, which is nothing but phi, whatever is calculated, minus phi c, what is the converged value where it should converge. So if we over relax, there is a chance of, so that is something which I mentioned in the previous question, that this is phi c and this is the last value. If I'm over relaxing, it may overshoot the converged value and then have to come back and then go this way, again overshoot, again come back. So this way it can oscillate. It can cause oscillations like this. And these are of course the iteration number k in the x-axis. So this is one of the disadvantages of over relaxation, and in that case it will keep oscillating like this without ever reaching the converged solution. So in that case, if I'm under relaxing, so okay, I'm drawing the same figure. So let's say if I'm under relaxing, then my rate of moving towards the converged solution may be slower, but I am slowly and surely getting towards it. Okay, so this is the under relaxed solution.
Sir, I have a doubt, sir.
Yeah.
Sir, you said previously that over relaxation means you are taking longer steps. So under relaxation is actually taking smaller steps.
Hmm.
How would that lead to faster convergence actually?
Yeah, that is so this example. So and I mentioned, it can lead to faster convergence. It can sometimes lead to faster convergence. So in cases where over relaxation is leading to these kind of oscillations, then it will take a much longer time to reach convergence because it is going back and forth about this converged solution again and again. So in that case, the under-relaxed method would actually reach convergence earlier than over-relaxed method. So in those cases, it will lead to faster convergence than over-relaxation.
Sir, any example is there sir, where we can actually differentiate between under relaxation and over relaxation, where over relaxation is actually converging faster?
Yeah, so this is a special case. Like if you over-relax too much, then this risk is there of fluctuating around the converged solution. Only in
Okay.
those cases, under relaxation would be giving you faster convergence, not in all cases. In most general cases, if you use a reasonable or optimal amount of over relaxation, then that is the quickest way of reaching convergence.
Oh,
Okay.
okay, okay. Thank you, sir.
All this is true only in the case of oscillations being built up.
So it is only for some cases.
Only for some cases, yes.
Okay, okay, okay. Thank you, sir. Thank you.
Okay. So that is why both option A and option B are, so both statement A and statement B are true. And in this case, the correct solution would be option D, picking both A and B, which some of you had picked. So well done. Okay. Any questions on this? All right. So things are clear. We will keep moving along. We'll move on to question number 5 now, which is asking us which of the following iterative methods is better at handling non-uniform meshes. Is it option A, point Gauss-Seidel method, or is it option B, line Gauss-Seidel method? Okay, we have one quick response in favor of option A, point Gauss-Seidel method. Let's see what others have to say. Again, in favor of A. We got a couple responses in favor of option A. Let's see what others have to say. Is it point Gauss Seidel method or is it line Gauss Seidel method, which is better at handling non-uniform meshes? Okay, another response in favor of option A. All right, so if we take a look at the solution, it is indeed option A. So those of you picked option A correctly. Good. So what is the reason behind this? Can anyone tell me? Any guesses? Because we need to look at the line Gauss-Seidel method, in which we do something like this. So let's say if there are 5 points like this. So this is our usual template: I comma j, I plus 1 comma j, I minus 1 comma j, I j plus 1, I j minus 1. All right. So in line Gauss-Seidel, we use 3 points at a time in a line and two others like in the transverse direction. So if we're doing an X sweep, in that case we pick these 3 points on the X axis and two on the Y axis, like this. And then we form equations, sorry, then we form finite difference equations from the partial differential equations, and then we solve them in different methods which we have discussed earlier. Now the issue here is that this is useful only if the delta x and delta y between all these points are uniform, and not only uniform, all these are rectangularly placed as well. Now imagine if there were 3 points like this in a domain something like this. So let's say we are using a triangular mesh like this. That is quite possible. Now, imagine trying to do line Gauss seidel with 3 points like this, which are not in a line in the first place. And uh, so, first of all, they are not in a single line, and they are not equidistant as well. So the delta x and delta y are all different. So in that case, so this is delta x1, this is delta x2, delta y1, and let's say, so this is the difference between these two, and in between these two there is some different delta y2. In that case, performing line Gauss seidel method becomes very difficult. Handling it, the bookkeeping part of it becomes very difficult. In those cases, point Gauss seidel method is much better. Does that make things clear? Am I making sense here? Okay. So if there are no questions, we will keep moving on. Okay. Is Damera? Thanks for that thumbs up. Okay. We will then move along. We'll move on to question number 6 now. Which is asking us which one of these. So here again, three different scenarios are given in options A to C, and option D is none of these. So you have to pick which of these are not governed by elliptic equations. So a few of them may be elliptic equations, some of them may not be, or it can also be that all of them are elliptic equations. In that case, you have to pick option D, none of these. So figure out this carefully. So the three situations given are option A, 2D incompressible inviscid flow. Option B is 2D incompressible but viscous flow. There is option C, 3D incompressible but inviscid flow. Or is it option D, none of these? Okay, so we have two quick responses in favor of option B, that is the viscous flow, 2D incompressible viscous flow. Let's see what others have to say. Which one of these are not governed by elliptic equations? Is it option A, 2D incompressible inviscid flow, 2D incompressible viscous flow, 3D incompressible inviscid flow, or is it option D, none of these? And some of you are telling that it should be option B, 2D incompressible viscous flow, right? Any other responses? Okay, so we got one response in favor of option D. There is none of these. Alright, shall we look at the solution now? Some of you are still thinking. Alright, so let's have a look at the solution. It's actually option D, none of these. So only one person picked this correctly. Well done. Now the thing is, the let's go through each of them. So option A is 2D inviscid flow, and all these are incompressible. So I'm not repeating incompressible again and again. So 2D inviscid flow. In that case, we can write down the equation using the potential function like this: the velocity potential function phi. So if it's inviscid, it's zero. Yeah. So this is a elliptic equation, all right. So this is elliptic. So the question in the question we have to identify which is not governed by elliptic. So since this is elliptic, this is not true. Uh, so for option C, let's look at option C first. So this is very similar. Instead of 2D, we have a 3D inviscid flow. So we just add another uh, term with respect to Z, and that becomes our 3D incompressible uh, and inviscid flow equation. Now, option B, the viscid case, in that case, we have to write it in terms of stream function because potential flow theory cannot accommodate viscous nature or rotational flow. So, if there is viscosity, there is a high chance there will be rotation, and the rotational flow, so if the flow is rotational, then velocity potential cannot exist. So these are basic fluid mechanics. So I will ask people to go and revise that if you don't remember. So phi cannot exist if the flow is rotational. That is the bottom line. So in that case, we have to use the stream function, and if it's rotational, then this vorticity term would be here on the right hand side, omega, and omega z. Z vorticity is what we will have here. And so this basically uh, comes from stream function vorticity formulation. So if you want to read up a little bit more on this, it's very interesting. You can go see how, from the Navier-Stokes equations we can eliminate pressure and form this stream function vorticity formulation. This you can find in any a bit advanced fluid mechanics book. Stream function vorticity formulation. Now this equation is again elliptic. It's not that it is not elliptic. So if we again cast it in that form, that what we had done earlier, the a into what was that, dou phi dou x square plus b dou 2 phi dou x dou y plus c dou 2 phi dou y squared plus something something. I'm just clubbing them all into D. Since these are second order equations, we will look at only the second order terms. There can be first order terms, the variable phi itself. I'm clubbing them all up into D. Okay. Now, if you're trying to figure out whether it's elliptic or not, we shall look at b square minus 4ac. What is the value of it? So in this case, for option B, this case, which we're looking at, if we put in a and b over here, the values of a and b are 1 each. Sorry, not a and b, a and c, and the value of b is 0. So b square minus 4ac simply becomes 0 square minus 4 into 1 into 1, which is equal to minus 4. Now this is less than 0, hence it should be elliptic, right? So option D, B is elliptic as well. So this also does not qualify as something which is not governed by elliptic equation. So all these three cases, options A to B, are all elliptic equations. Hence, the proper answer to this should be option D, none of these. Okay, I hope that clears things up. Any questions from anyone? Okay, so then we will move along. Move on to question number 7 now, which is asking us which one of these methods have more data storage requirements. Is it option A, Jacobi method, or is it option B, Gauss-Seidel method? Okay, we have one quick response in favor of option A. Not only one, many quick responses. Okay, we got a lot of responses in favor of option A. Let's see what others have to say. The Jacobi method seems to be the culprit here. Which of these methods have more data storage requirements? Okay, so let's have a look at the solution quickly. It's indeed option A, Jacobi method. So well done, all of you. Thing is, in Jacobi method, as we discussed earlier as well, we find the new data. So I'm writing this in this form. So this matrix comprises of phi11, phi12, phi like this. Okay, and these are all at the k plus 1th iteration. And we also, and this is a function of another matrix which is all the values at the kth level, that is the old data. So here also we have all these phi ij at the kth level, and these are phi ij's at the k plus 1th level. So we need to maintain two matrices, these two matrices of old data and new data at all times. Plus other things are there, that's different, but the data points themselves are these two. So in industrial CFD simulations, there are millions of data points which are involved. So these matrices would consist of millions of points, and if you're trying to use Jacobi method, we need to store twice of that. But in the other case, in this Gauss-Seidel method, we only maintain one matrix, and there we have, let's say, if you are going from the bottom, so at this point, let's say at phi ij at k plus 1, we are trying to measure, and earlier than that, let's say phi I, any other point earlier than that, let's say this one, I'll call this phi I minus n, comma j minus n. Let's say this is any earlier point. This is also at k plus 1. This has been previously calculated. And let's say some other point later on. This will be calculated later on. That is phi, let's say I plus some n2, comma j plus m2. This is not calculated yet, so this is still at the kth level. So there is only one matrix in Gauss-Seidel method which we keep on updating, right? So the Jacobi method uses data which is twice the Gauss-Seidel method, at least from the data storage point of view. Does that make sense? So Jacobi method, in addition to having slow convergence, it has more data storage requirements as well. So you can imagine why this is not so popular anymore, right? But anyway, it's a simple method and it's important for learning CFD. Okay. Any questions, anyone? All right. So if there are no questions, we'll keep moving along. Okay. So the question remains the same. The options change now. Which one of these methods have more data storage requirements? Is it point Gauss Seidel method or is it line Gauss Seidel method? Okay, we have a few quick responses. Most of them in favor of option A and one of them in favor of option B, the line Gauss Seidel. So we have a divided crowd. Let's see if anyone else has anything to say. Think about this carefully. Okay, so let's have a look at the solution. It's actually option B, line Gauss Seidel method, not A. So why is it so? So as I told earlier, in point Gauss Seidel, I call this PGS maybe. So we have this only one matrix, which is m cross n, of course. So I have something like phi I 1 comma 1, phi 1 comma 2 dot 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 phi 1 comma m. Similarly, some phi ij, and in the end I have phi m comma n, let's say. So this is how the matrix looks like, and we keep updating values. So phi I comma j k plus at the k plus 1th term, and only this value I will update based on all the other values that I have. Some of them may be at the kth level, some of them may be at the k plus 1th level. So updated or old doesn't matter, but I'm only using one matrix which is of the size m cross n. So this is the data storage requirement for point Gauss Seidel. Right. Now bear with me and come to line Gauss Seidel. So in line Gauss Seidel, what do we do? So let's say we are considering X sweep only. So using these three, we try to form an equation using these three and additionally these two other equations, these two other points. So this becomes something like phi alpha I minus 1 j plus beta uh, I comma j plus gamma phi I plus 1 comma j and some delta over here. Now delta is a function of some phi at the kth level, and these are all unknowns at the k plus 1th level. So delta is again some known quantity, some sum of some combination of known quantities at the kth level. And I have multiple such equations. So I'll just call them alpha 1, beta 1, gamma 1. Similarly, I'll have alpha 2, beta 2, gamma 2. And similarly, I minus 1, comma j, I comma j. Okay, not j. Now I'll go to j plus uh, 1th level. Is it? Am I doing this correctly? Or no, sorry. So if you're doing a X sweep, so then we'll just shift these values. Okay, I'll just check. Yeah. So while X sweep, we keep on moving like this. So after having used these 3 points, we will move to these 3 points then. So this will now become I comma j. This will become I plus 1 comma j, and this will become I plus 2 comma j, and again some delta 2, which are again comprised of phi quantities at the k plus 1th level, and these are again at k plus 1th level, the unknowns. right? So in this way, it will keep on going, and we will basically form a matrix equation like this. Here, all the phi k's are there, and the length of this vector is also m com. So this is, let's say, one vector of I call that p quantities. So there are p quantities here. The vector is p unit long. These are at k plus 1, sorry. And this is again phi at k, and this is again p items long. And what is p? P is actually equals to m comma n. So here I now have to maintain two vectors, one old and one new, and all of them have m cross n items within them, p items, which is equal to m into n. So in line Gauss Seidel method again, the data storage requirement is double that of point Gauss Seidel method. Does that make sense? And these are all, betas, alphas, and gammas. Any questions, anyone, on this? So line Gauss Seidel method is actually quicker than point Gauss Seidel method, but the disadvantage is this extra data storage required. Okay. So if things are clear, we will keep moving along to move on to the second last question of today's session, which is asking us what is the correct order of steps in TDMA. What is TDMA? Can anyone tell me? You can type in the chat box or you can unmute and answer as well.
Tridiagonal matrix algorithm.
Correct. Good. Tridiagonal matrix algorithm. This has another name as well. What is that name? This is named after this scientist. Yeah, someone has written in the chat box correctly. That is Thomas algorithm. Okay, so this is actually used for solving these line Gauss Seidel method type techniques. So this is asking us what is the correct order of steps in TDM. There are three steps given here in Roman numbers 1, 2, 3. You have to pick out the correct order from the four options given below. So these steps are step 1, back substitution, step 2, forward elimination, step 3, conversion to upper diagonal matrix, and the different order of steps, the combinations given in the four options are option A 1, 2, 3, option B 3, 2, 1, option C 3, 1, 2, and option D 2, 1, 3. So figure out the correct way of doing things, and that should point you to the correct combination in the options given below. And once you have figured out the solution, you can always type in the chat box. So we already have two quick responses, and both are in favor of option D. Let's see what others have to say. Okay, one more option D. One response in favor of option B. It is 3 to 1. We have a split in the crowd. Let's see what others have to say. Okay, so let's have a look at the solution. It's actually option B, 3 to 1. So why is it so? Let's discuss the tridiagonal matrix algorithm in brief. So basically what happens is we form a matrix which looks something like this. So we have some unknown values here and another vector over here. So I'll call these d1, d2, dot 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 dn, and here we have a tri-diagonal matrix. So we basically form three diagonals, which look something like a1, a2, a3, dot 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 an, and this is the prime diagonal, and we have one. Or the leading diagonal as well. We have two more diagonals, one above it and one below it, which looks something like this. So B1, B2, B3, dot 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 Bn, or actually it will be n minus 1 maybe. Anyway, and we have something on top of this C1, C2, C3, dot 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 Cn minus 1. Yeah. So, and anyway, and here in this vector, we have all the uh, data that we want to solve for. Okay, anyway, so that's not important. So here we have some data like T1, T2, dot, 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 Tn. Now, the first step is the step 3, the conversion to upper diagonal matrix. What we do is we simply take each row and normalize it with the leading diagonal term. That is, we divide with the leading diagonal term and subtract it from that row. So it's a row operation that we go through, and that gives us, that actually removes this. Let's see. So that actually removes this sub-diagonal terms. And we finally uh, get something like, let's say, A1 star. So these values now get changed a little bit. Dot 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 AN star. The super diagonal terms remain, but they also get changed. So this will become C2 star dot 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 Cn minus 1 star. And this vector remains intact, T1, T2 to Tn. These terms again get changed, d1 star, d2 star, dot dot dot, dn star. So what operation do we do here? We take each row, let's say the ith row, we divide it by the leading order term. So the aii we divide it with, and so ri, and we subtract it from the original one. So sorry, not aii, basically bii. So that basically makes all these terms 0. Right? So Ri becomes this. Anyway, so that doesn't matter. We get all zeros here. So, and this becomes a upper triangulated matrix, as we know. So or the upper diagonal matrix. So this is the first step, conversion. Then comes forward elimination. What is forward elimination? So if we consider only the last row, we know that an star Tn is equal to Dn star. So we simply get Tn equal to Dn star divided by An star. We got this value. This was unknown earlier, it became known as of now. And the next step is to move on to the next column then, or sorry, the next row then. Then it becomes a n minus 1 t n minus 1 into plus cn I'm not writing the stars anymore. So Cn Tn is equal to Dn minus 1. Here comes, so this step is the forward elimination. And then comes the back substitution where you know the value of Tn and we substitute here to find out the value of Tn minus 1. So in this equation, everything else is known, just Tn minus 1 is unknown. And we keep doing this and keep moving, we start from the back and we keep substituting values and keep moving towards the starting end. That is, we start at n and move towards 1. So that is known as the back substitution step. So the correct order of steps is 3, 2, 1. Option B is correct. Okay. Any questions on this? So for more details, so I can understand that the math which I worked out here is very ugly and all over the place. So I would definitely suggest you to go look at some better sources and try to understand how TDMA is actually done. And one good practice would be to actually write a code for TDMA in whichever coding language you are comfortable with. So this is a very simple, very quickly it can give you the results, but writing the code by hand once is a very good practice. So I would suggest that. And that way things become more clear as well if we do things by ourselves. Okay, so good. So if there are no questions, we will then move on to the last question of today's session. Now this is the match the following type of question. We have three items on the left column and three items on the right column. We have to match them with each other appropriately. Now the thing is, what are these items? So the left column has solution methods and the right column has their disadvantages. So you have to match them with each other. The left column consists of option A, over relaxation, option B, point Gauss Seidel, option C, line Gauss Seidel, and the corresponding disadvantages are disadvantage 1, the non-uniform grids and irregular geometries. Option 2 is may not converge. Option C is matrices which are not diagonal dominant cannot be solved using that method. And there are some possible combinations also given in the options below. So option A, A1 B sorry A1 B3 C2, option B A3 B1 C2, option C A2 B3 C1, and option D A2 B1 C3. So try to match each of them and that should give you the correct combination. Okay. We have two responses in favor of option B. Let's see what others have to say. So some of these are actually, hinted to in the earlier questions which we solved today as well. So these should not be completely new altogether. Right. So let's do them one by one. So over relaxation, what is the disadvantage of that? Anyone? So for solution method A, over relaxation, which one is its disadvantage? 1, 2, or 3? So we said that in case of over relaxation, it may set up fluctuations like this about the converge solution. In that case, it may not converge, right? So A corresponds to 2. Now, solution method B, point Gauss Seidel method, which is What is the uh, pitfall of that? Okay, let's go to option C first. So line Gauss Seidel, what is the disadvantage of that? This was one of the questions today. So non-uniform grids and irregular geometries, it cannot handle well. Okay, and that leaves us with one more option. Point Gauss Seidel is that the matrices which are not diagonal dominant cannot be solved properly. So the correct order then becomes A2, B3, and C1. Is this combination available in any of the options? It's actually option C, right? A2, B3, C1. Yeah. So let's have a look at the solution. Yeah. So it's actually option C which is correct. Okay. Any questions, anyone? All right. So that brings us to the end of today's session. So thank you all for participating actively. I'll see you again next week.
Thank you, sir. Thank you. Thank you, sir.
Thank you, sir. Okay.
Okay, sir. We are leaving.